It will last about 30 seconds. Hello. This area of the tape should be used to adjust tracking and audio level. It will last about 30 seconds. Great Plains Research and Development presents the EZRII Upgrade Kit Development Contract. Video Contract Review. Developed December 20th, 1990.
I'm Carl Gibson, Chief Financial Officer of Great Plains Research and Development. GPRD submitted an unsolicited proposal to engineer an upgrade kit for the extended Zip Retrofit. The EZRII Retrofit kit is deployed to 400 multi-position letter sorting machines. This unsolicited proposal resulted in a development contract. This statement of work authorized an ad hoc engineering development of the EZRII. This development was a result in an upgrade kit for field deployment to the 400 EZRII-based MPLSMs. The primary requirement was the development of enhanced data collection and report generation capability. This videotape briefing was prepared as an end-of-contract review. This review was determined to be an excellent means of transferring knowledge. This knowledge was learned from our experience gained in the ad hoc engineering, kit manufacture, installation, and on-site training. This information will be invaluable during the production and deployment phases of the EZRII life cycle. The MPLSM has been sorting mail for over 20 years. Approximately 900 MPLSMs are deployed in over 300 post offices. 400 of these have the EZRII Retrofit sort electronics. The MPLSM is the backbone of the semi-automated mail sorting in the Postal Service. Recent purchases of the EZRII MPLSM have been made in the late 1980s. This means that many of these MPLSMs have low operating times. A general misconception exists that the MPLSMs are obsolete. First, it should be noted that no MPLSM, even those purchased 20 years ago, exists as delivered. All of the Postal Service's MPLSMs have undergone overhauls by trained Postal Service overhaul teams. Overhauls occur every 2 to 3 years, and these overhauls included updates and modification to keep the MPLSM in tune with present sorting technology. The biggest advantage of the MPLSM is its ability to handle mail from postcards to small books, such as TV guides. Additionally, the MPLSM has been adapted to many forms of optical reading and coding equipment. Much of the sorting advances and modifications to the MPLSM over the last 20 years have been mechanical simplifications to improve reliability. These simplifications were made through the use of electronics to replace mechanical sorting components. This report provides a graphic description of the results obtained from the GPRD EZRII development contract. This video report will start by introducing the multi-position letter sorting machine. A visual description of the general mail flow of the MPLSM is provided. This description explains the excellent mail handling capability of the MPLSM. The existing EZRII control electronics are then described. This is the control electronics in place before GPRD developed the EZRII upgrade kit. During this EZRII introduction, the components replaced the new EZRII equivalents will be noted. The EZRII replacement components are a result of advanced engineering of hardware and software trade-offs. The engineering of the EZRII design was performed as an ad hoc development with many comments from the simple, "This function works poorly in the present EZRII," to problems found during the 12 field beta test site installations. The most important development was data collection. This was the source of financing that drove the EZRII development contract. Additionally, it should be noted that many of the features of the EZRII design are future options that can be added as required. These options can improve the productivity and mail handling options of the MPLSM. The result of this development is detailed by a visual tour and description of the EZRII components. This tour will describe the components of the EZRII and by reference what components of the old EZRII they replace. The statement of work required installation of the first 3 Postal Service sites by GPRD. installation procedures were developed to allow postal technicians to install the EZRII upgrade kit. This installation procedure is described. Many problems, however, were encountered during the attempts to have field technicians install the EZRII. Suggestions for the production contract installation requirements are presented for incorporation in the production contract. It should be noted that all but 2 sites were installed by GPRD. This was due to problems encountered during installation. These problems were associated with variations in the MPLSM or the existing EZR. Training for the beta test sites were conducted at all 12 sites. GPRD developed the training classes and the material presented under the Statement of Work guidelines. The training course is described and problems that were uncovered are presented. Problems should be reviewed and corrections incorporated in the production Statement of Work. Most importantly, the training period of 2 days we recommend to be extended to 3 or preferably 4 days. The software development for the EZRII is very simple to operate with point-and-pick menus. This has been offset by many advanced functions of the EZRII. Most important is the real-time status display features of the EZRII. These features can detect productivity problems on the MPLSM and allow real-time correction. Used effectively, this feature can alone improve productivity of the MPLSM by 10 to 15%. This is a significant return for maybe 4 days of supervisor training. Finally, the contents of an EZRII upgrade kit are displayed and discussed. Included in the task of the EZRII development was the engineering of a technical design package to allow the production deployment of this design as a field upgrade kit. This technical data package was developed to level 3 standards to allow open competition for the manufacture of the EZRII upgrade kits. This package includes full documentation for the manufacture of all custom integrated circuits and printed circuit boards developed. The EZRII upgrade may look like a PC with software, but it is in fact a formidable industrial process control computer. There are 14 microprocessor-based cards in the EZRII upgrade kit. These cards are used to replace and upgrade the functions of many existing EZR components in the MPLSM. Let's get started with the introduction of the mail flow and operation of the MPLSM.
The mail trays are unloaded onto the ledges of the 12 MPLSM consoles in a manner that maintains the facing and orientation of the mail. The ledge-loaded mail is then transferred to the feed table on top of the console. These mail loading operations are performed by typically 2 ledge loaders per MPLSM. The ledge loader personnel are off-duty console operators which rotate between ledge loading, sweeping the MPLSM bins, and console keying. Mail from the console feed table is simulated into a single piece by a mechanical pick-off arm. This pick-off arm then places the mail piece in front of the console operator. Console operators presently key part of the zip codes on a mail piece at a 1 letter per second rate for outgoing mail. Outgoing mail is mail for which the 5-digit zip code is sufficient in itself to provide a complete sort. Operators are also trained using memorized schemes known as secondary schemes to key mail based on local mailing addresses. This keying mode is used for incoming mail that is to be sorted to delivery clerks in the local post office. The 5-digit zip code is not sufficient for this sort as it takes mail to a zone in which there can be 10 to 50 carriers. Scheme operators are typically trained to sort 5 secondary schemes with 100 memory items per secondary scheme. One of the advanced features of the EZRII is the alphanumeric address data entry and sorting. Typically, this is the thousands and hundreds of the block number and the first and last letter of the main street name. This approach, called extraction keying, is very effective. The existing 20-key piano keyboard is initially used with 6 of the alphanumeric letters, such as X, Q, Z, duplicated with other letters. The EZRII microprocessor-based console interface card can take in direct parallel input from a true alphanumeric keyboard and has 256 kilobytes of conversion memory to provide very sophisticated extraction key systems. The queued mail is then transported into the MPLSM, where it is deposited into carts for transport around the MPLSM to the sorting bins in the back of the machine. Note the dropper mechanism which operates the mail pieces into a fixed compartment of the letter carts. There are 161 letter carrying carts in the MPLSM, each of which has 12 letter compartments. There is one letter compartment for each of the 12 consoles of the MPLSM. Each console drops one letter in each cart in an assigned compartment. The compartments have spring-loaded door trip levers that can be opened to let the mail pieces fall out through the bottom of the letter compartment of the cart into a sorting bin. The original carts are made of metal and have an aluminum finish. The latest manufactured carts are made of plastic and appear black. These carts are lower cost to produce, but have caused static problems with the older EZR design, causing missorting. The EZR2 design is resistant to this problem and operates very well with full load of 161 plastic carts installed into the MPLSM. The MPLSM has 277 standard mail sorting bins, each of which can hold approximately 300 pieces of mail. The bins are manually cleared by personnel called sweepers. Sweepers are rotating console keyers that rotate between console keying, ledge loading, and sweeping duties. The letter sorting bin maintains alignment of the mail to assist in future mail sorting operations. The mail is tripped from the passing letter carts by electronically controlled rotary solenoids, which trip the door latches. The mail piece then falls by gravity into the letter bin chute, which maintains spacing, and finally into the bottom of the bin. Mail collection into the bin is then removed by the sweepers. To prevent overflow of the bins, photo sensors called bin full sensors are in place. These sensors are provided to inform the control electronics that the bin is full. The EZR2 design allows 10 extra letters to fall into the bin after an initial bin full detection, while the EZR design bypasses all mail at this point. This feature greatly reduces the bypass mail of the original EZR, which, as noted, immediately blocks further mail to the bin. The sweepers remove the mail from the bins and refill the mail to check for obvious mail sorting problems. The mail is then placed into the outgoing mail trays in the back of the MPLSM for further processing.
The existing EZR design was developed 10 years ago and is one of the first microprocessor-controlled developments of the Postal Service. The design consists of a supervisor's terminal using simple 25 by 80 character alphanumeric text displays. The terminal is connected to the control electronics by an RS-232 serial link. The MPLSM supervisor controls the operation of the EZR by commands entered into the terminal. Status and reports are returned on the display of the terminal. Mass storage of the EZR program, sort scheme storage, and report data is provided by the disk drive module. The disk drive module contains two 90 kilobyte single-sided low-density 5 1/4 inch floppy disk drives. An alarm and status reporting module is provided to audibly and visual report EZR status and power backup operation. The combination of the terminal, disk unit, and alarm panel are replaced in the EZR2 design by a process control computer based roughly on a PC-AT computer layout at the software compatible level. The EZR dot matrix printer is an 80 character per second narrow carriage unit designed to print 80 columns of 5 by 7 dot characters. The printer is connected by RS-232 serial link to the EZR control electronics. The EZR2 design provides an improved performance printer. The EZR control electronics are located in the central control rack inside the first module of the MPLSM. The central control rack contains 6 large electronic printed circuit cards. These cards perform console operator key conversion to bin density, induction into the sorting module of MPLSM, sorting of the mail piece to the destination bin, data collection, and report generation of the EZR. The EZR master processor is based on a 9900 microprocessor and has 4 kilobytes of local memory. 2 serial ports are provided to connect to the supervisor terminal and the EZR printer. A switch to select between maintenance and mail processing modes is also included. The design of the EZR is a single function and cannot perform maintenance and sorting at one time. A 32 kilobyte static RAM access memory card is provided to hold, sort schemes, sort data, data collection, and transfer memory blocks to exchange data between the central control rack cards. The memory card is based on 10-year-old technology and uses more power alone than the entire EZRII process control computer. The disk interface card is used to interface to the disk box in the supervisor's panel. This card interfaces the two 90 kilobyte disk drives to the EZR master processor. The sort processor card is a bit slice implemented high-speed processor for performing the real-time process of mail sorting in the MPLSM. This card uses a set of memory blocks and 32 kilobyte memory to generate a mathematical model of the MPLSM from which the sorting status of the bin trips is developed. Communications to the actual interfaces between the EZR and the MPLSM hardware is made by this communications bus interface card. This card drives a 13 twisted pair wire high-speed parallel communications bus which connects to the 7 bay control units in the MPLSM modules. The card transfers data collected by the bay control units to a 32K memory expansion place. This data is then used by the sort processor to generate sort outputs to the 32K memory. This sort data in the 32K memory is then transferred back to the bay control units. Finally, there is a card to control the activities of the central control unit. This card is the decoded central control unit controller card and provides a bus reset, card, bus attribution, and other timing and control functions for the central control unit backplane bus. As a note, the entire function of this central control unit has been replaced under this developmental contract to a single printed circuit card called the coprocessor card. The EZR bay control units form the interface between the electronic control and the mechanical components of the MPLSM. The bay control units contain interface cards to receive key data from the consoles, status from the MPLSM, and generate sort signals to the bin trips to deposit mail in the sorting bins. There are a varying number of cards in the bay control units depending on the number of items to be interfaced at the location in the MPLSM of a particular bay control unit. The typical number of cards is 6 in a bay control unit. The rack interface card connects the bay control unit interface cards to the 13 twisted pair wire bus from the central control unit communications bus card. This card is common to all bay control units. There are 3 bin trip interface cards in each bay control unit, each interfacing to the bin full and bin trips of the MPLSM. The bin trip card is read to obtain the bin full sensor status for the sort processor. After the sort processor generates sort information, it is written to the bin trip card. The bin trip card controls the bin trips that open the letter compartment doors and sort mail into the sorting bins. Each bay control unit has a general interface card which provides miscellaneous inputs from the MPLSM and console interface cards. The general interface card provides input status from the consoles, fault detectors, and the MPLSM transport motor. The console cards interface the console keyboards to the EZR control electronics. The keyboards present keys to the existing console interface card, which simply converts these key entries to coded values which are buffered by the general interface card. There is 1 console card in 2 of the bay control units and 2 console interface cards in the remaining 5 bay control units. This equals the 12 consoles of the MPLSM. The last card present in the bay control rack is the chain position sensor card. The geometry used to control electronic sorting of letters in the MPLSM is the conveyor chain that transports the letter-carrying carts. The chain position sensor card obtains motion information from 4 rotary motion encoders, 1 on each level of the MPLSM. Alignment data for the encoders is obtained from a link 0 magnet as it passes 0 position detectors on each level.
Hello, I am Charles Winters, Project Manager and Chief Engineer on the EZRII project. The unsolicited proposal, which resulted in the EZRII development contract, was developed under my direction. My background of working with the Postal Service from 1969 to 1980 on the MPLSM and its modifications provided me with insights necessary to develop this unsolicited proposal. The EZR was originally developed as the ESP ZMT elimination, or the acronym EZL. The EZL concept was the consolidation of many modifications to the MPLSM that had occurred over the 1965 to 1978 time period. These modifications transformed the MPLSM from a mechanical-based sorter in 1965 to an electronic-based sorting machine in the mid-1980s. Some history of these modifications was necessary to understand how the ad hoc development of the EZR2 was directed. The development of the future EZR2 upgrade to the MPLSM required a detailed understanding of the history of the MPLSM. The original MPLSM was totally mechanical, with only a few electrical solenoids and relays. The sort control was obtained by mechanical escort memory. The zip mail translator, developed in 1969, allowed the use of less trained mail clerks on the MPLSM and paid for its deployment and development by these labor cost savings. The electronic sort processor, developed in 1972, allowed the MPLSM to shed the mechanical escort memory. The ESP retrofit was only economically feasible due to the high maintenance cost of the mechanical sort components of the MPLSM. The EZL development was unable in 1978 to find a problem to be a solution for, even though some significant future problems were seen on the horizon. This was due to the fact that the existing ESP and ZMT, along with their associated modifications of edit, ADAP, microkey, were performing all functions sufficiently well that they did not need to be replaced. With the advent of ZIP plus 9-digit zip codes, this situation changed. The EZL became known as the Extended Zip Retrofit, or EZR, and was developed to allow extended sort scheme operation using large sort schemes up to 4 numeric keys. The ESP and ZMT were limited to a 3 numeric key maximum, and most importantly, 8 kilobytes of sort scheme translation memory. This limited memory severely restricted the development of complex sort schemes. Many of the features planned for the EZL were not implemented to reduce the technological risk associated with these features. The EZR had to reliably perform the primary task of ZIP plus 4-digit mail sorting. As a result, many features were left out. The original EZL design, the elements that were not implemented in the EZR design, have been implemented in the new EZR design. This historical review of the MPLSM history, and in particular the EZL, has resulted in many improvements that would have otherwise been missed. The financing of the EZR2 development was prompted by the lack of detailed data collection features in the EZR design. These features were originally provided by the Automatic Density Analysis Profile Technique, or ADAP. The ADAP was used by the ZMT and later by the microkey-based zip data logger, both of which provided mail flow density information. This density information is used to assign sorting bins based on the amount of mail to each zip code. Since the MPLSM has only 277 bins, and there are thousands of zip codes, it is necessary to assign multiple zip codes to a bin. The data provided by the EZR2 will be used to efficiently define this sort breakout. Additionally, the EZR2 software will allow the analysis at the district or region level rather than at a single post office level as provided by the ADAP. This larger area data consolidation was initially tested in the microkey ZDL design using the Zentate Southern Region-based report software. It is important that the sorting of the MPLSM in many offices work together for the overall sorting performance rather than performance of a single post office. The large number of bins in the MPLSM, in comparison with all other sorting equipment in the Postal Service, tends to allow a single office to, in a single sort, break out many of the local office separations while still meeting a basic level of external breakouts. The funding of the EZR2 was not limited to the development of only the data collection features. This allowed GPRD to additionally develop many other features. This ad hoc nature of the contract was very interesting for postal contract management. The contract literally said, "Make a better mousetrap." I must say that the Postal Service personnel handled the process of killing the engineers very well. This point of killing the engineers is defined as the time when the process of engineering development to the EZR2 design were stopped and the design frozen. The timing was chosen very well. The EZR2 documented design is now operating at 12 post offices and has over 18 machine years of operation. During this period, only 2 EZR2 card failures and 3 off-the-shelf equipment failures have occurred. None of these failures affected mail sorting as they were offline problems. In fact, 2 were during installation test periods while GPRD was on site. One of these was caused by an electronic technician raising the voltage on a power supply to an overvoltage condition. There are some caveats that must be talked about at this point, as the present testing of the EZR2 is for the original function of the EZR2. The EZR2 does a very good job of data collection and report generation, as that is what it was purchased for. But the discussion for the present deployment indicates that alphanumeric extraction keying of mail is the primary reason for deployment. The EZR2 is designed for alphanumeric extraction keying, and in fact, GPRD has demonstrated software performing 4- and 5-digit alphanumeric keying. This software is operating at the Oklahoma City Post Office, which is the GPRD's primary test site for the EZR2. There are many design approaches to perform extraction keying with the EZR2 design. The approach in Oklahoma City was the method discussed by the Postal Service, which GPRD has recommended against. During the design and testing in Oklahoma City, we found that the Postal Service approach has many problems. These problems can be solved by using the EZR2 design as it was intended. To explain this and other features of the EZR2, it would be necessary to have a basic, non-technical understanding of the EZR2 design, and more importantly, what the EZR2 is and is not. The design of the EZR2 is modular, meaning that the EZR2 can be deployed without all of the cards and cables developed under this contract. As the modules are removed, so are many features and, more importantly, the sorting reliability of the EZR2 design. Many problems of the EZR design that cause problems are solved by embedded solutions in the EZR2 cards. The information needed to make an informed decision of what to include or exclude will be provided by the following description of the EZR2 design. The EZR2 design was developed using computer-aided design tools, also known as CAD. The workstation beside me is a 19-inch high-performance full-code design developed at GPRD. GPRD's 6 CAD workstations network to a 450 megabyte file server, which supplies multiple printers and plotters as output devices for the CAD system. Remote communications are also provided to allow transfer of data to and from support companies used by Great Plains Research and Development. Both the hardware and software of the EZR2 were developed on this CAD system. We use the CAD system to describe the design of the EZR2, as the CAD system can generate multiple views and rearrange data efficiently. This will allow the display of information that cannot be easily generated by any other way for this videotape. The first element of the EZR design we will review is the block diagram supplied as USPS 1001886, a drawing in the delivered technical data package. This drawing provides a block diagram of the old EZR design, and adjacent to this design, the EZR2 kit block diagram. This block diagram, as can be seen, is very detailed. The diagram shows all components of the EZR design down to the bin trips used to open the cart compartments and sort the mail. This rather fuzzy level is the best place to start the description of the EZR2 design. The first observation is the large area covered by the EZR2 kit control electronics. I will highlight this area now by using our little cursor to move around. As you can see, the cursor moves quite a ways down through the LSM area. This area being surrounded is the actual one-to-one area where the kit is occupied throughout the MPLSM. The MPLSM is roughly 80 feet long by 9 feet wide, excluding the consoles, and 11 feet high. The consoles extrude another 9 feet from the front side of the MPLSM main frame. The EZR2 electronics are spread the entire length of the MPLSM and mixed with the EZR components. This approach of distributed process control was the best means of connecting the many bin trips, full bin sensors, and console interfaces to the central control electronics. The original ESP design did not use this approach and resulted in very significant cabling and noise interference problems. The MPLSM and the EZR are modular in that the MPLSM is manufactured and installed in modules. To complement this, the EZR design mounts a bay control rack in each MPLSM module. Each of these bay control racks are self-standing, including power supplies. Using the highlight cursor, I will outline one of these modules, which is being shown here as an area in a vertical sense. This actually is, to some degree, the way in which the modules of the MPLSM are arranged, as they are taller than they are wide. Connection of the 7 bay control racks is made with a single 13 twisted pair communications bus cable. This cable proceeds from the central control rack, being highlighted now, to the first bay control rack, through this rack, to the next rack, then again to the next rack, in this looping fashion. This looping fashion proceeds through the machine. As you can see, there are 7 bay control racks being highlighted, to the last bay control rack, which is equipped with a terminating resistor. Actually, the MPLSM has 2 additional modules. These are the motor and turn ends, but these 2 modules do not contain any sorting relating components in them. The block diagram clearly shows the 7 modules of the EZRII design. These modules are almost identical, allowing considerable interchange of common components and simplified troubleshooting. This was a major element of the EZL concept that was carried over to the EZRII design. The ZMT and ESP designs fortunately were very reliable, as a failure of either was a major troubleshooting job. Another general element to observe at this level is the central control rack, being highlighted now with our cursor. The EZRII design used a rack located in the last module containing the sort and user interface processors. This unit consists of 6 printed circuit boards of 8 by 13 inches in size with an average of 80 integrated circuits. Attached to the central control rack are the disk interface, alarm panel, and supervisor terminal. Note the EZRII retrofit kit is displayed along the bottom of the EZRII components in the rough location of the final components in the design. EZRII components are located in all parts of the MPLSM. The EZRII uses a process control computer to replace the supervisor, terminal, alarm panel, and disk box. The coprocessor card replaces the central control rack. There are 12 console and 1 CPS cards in the EZRII kit, which replace the bay control rack mounted cards of the EZRII design. Additionally, a local area network cable and roll-around table terminal cables are provided to connect the new components together. Below this area are the block diagram of the EZRII console, CPS, and coprocessor cards. Let's look at the central control rack in detail, as this rack contains the primary control processor of the old EZRII design, which was replaced by the coprocessor. The central control rack is located in the last module next to the bay control rack in that module. The rack contains 6 printed circuit cards of 8 by 13 inches in size. These cards perform all the processing of the EZRII design. There are 2 TI 9900 microprocessors and 2 bit slice processors in the EZRII design. The first card in the communications bus controller, being highlighted now. This card interfaces the 13 twisted pair interface cable to the bay control racks from the central control rack. As you can see here, this is the first rack control card. The cable proceeds over to the communications bus interface card. All transfers are automatically performed between the 32K memory and the bay control racks. This transfer is performed by a bit slice processor with dedicated read-only memory programming. The sort processor card, located directly above the communications bus interface card, uses read-only memory program microcode. The sort processor uses the memory images contained in the 32K memory card to perform the actual sort operation of the MPLSM. This includes performing the CPS to bin reference calculations, letter compartment to bin alignment calculations, and full bin interlock functions. Only the translation of keystrokes to bin destination is not performed by the sort processor. The dedicated CCU bus controller card performs the traffic cop function of the central control rack. Since there are 4 cards in the central control bus that can access the central control bus, this card provides the necessary arbitration to prevent conflicts. Additionally, the card is programmed using combinatorial logic to assign a higher priority to the sort processor and the communication bus controllers as they transfer more data than the other cards. The 32 kilobyte memory card is the center of all processing in the EZRII design. All data transfer and processing occurs in this memory. Due to memory mapping and bus address restrictions, only 28 kilobytes of this memory is actually used. As a result, the total scheme memory available to the EZRII is limited to about 24 kilobytes. This was enough to allow 4-digit numeric keying with multiple sort schemes, but not enough to perform alphanumeric extraction keying. The master processor provides all user interface to the EZRII and key-to-bin translation. The supervisor, roll-around table terminal, and the EZRII printer are driven from this processor. Additionally, report generation can be performed as an offline function. The edit function used to monitor the operators was also performed by this processor. The TI 9900 microprocessor was used, which unfortunately does not have a good software development base or operating system. This was the reason for changing in the EZR2 design to the more supported 8386 and 8186 Intel processors. The disk interface board provides I/O connection with the disk box. The disk box contains 2 5 1/4 inch disks rated at 90 kilobytes per disk drive, although the disk drive used in the box has changed over the deployment of the EZR, and some systems have higher capacity drives. The disk is used to load the specially programmed EZR operating system, or more accurately, the EZR applications program. The disk format of the EZR can be read by the EZR2 design, so that this existing sort schemes can be transferred over with little effort. This is not normally done with the EZR2, as a separate electronic scheme manager, or ESM program, has been written by the Postal Service to perform this function. Next, we'll pan over to the central control rack located in Bay C3. The reason that we use the Bay C3 rack is that this particular rack contains the majority of cards used in the system. The communications bus control card communicates through a 13 twisted pair cable that loops down through each of the 7 bay control racks. The last bay control rack has a terminating resistor to terminate this bus. All bay control racks have a rack control card. This card converts the noise-immune differential multiplex signals of the 13 twisted pair cable into single-ended TTL signals. These signals are further decoded and buffered and then placed on a local backplane for the input-output cards of the rack. The decoding provided by the rack control card, including I/O card selects and data buffering, to isolate input and output data. This allows the I/O cards of the rack to provide simple I/O functions with minimal bus-related tasks. The rack control card is not changed by the EZR2 design. One note here is in order. The original EZR design did not use shielded cable for the twisted pair cable. Second, the ground reference between the bay control racks is a small conductor that resulted in significant ground offset. This is aggravated by inductive coupling noise from 120-volt AC switch solenoids in the LSM. This causes momentary DC offsets that saturate the receivers of the rack control card and momentarily prevent reliable communications. The EZR2 design should also include a replacement shielded cable for the 13 twisted pair line, along with the local area network cable. The next card is the general interface card. This card provides input buffering for console and MPLSM related signals in this module. The output of the 1 or 2 console interface cards, called keyboard interface cards in the drawing, and EZR and AC converted module signals are provided by a level shifting card, not shown on the block diagram. The keyboard data is buffered in this card by 2 16-key first-in, first-out buffers, one for each console in a module. The general interface card is not replaced in the EZR2 design, although it should have been. There are at least 3 versions of this card which are showed up during deployment of the 12 EZR beta test sites. The card's input buffering is noisy and has several race conditions that need to be fixed by back-to-back clock registers. In particular, the EZR2 console interface cards work reliably with only one of the 3 designs. Time to debug and reasons to provide possible fixes was not undertaken. Even when used with just the coprocessor card and EZR2 software, the general interface card causes problems due to the much higher scan and access speeds of the newer technology. The next card in the console interface card, which interfaces to the console mail clerk to the EZR system. This card receives the lockout signal used for console process timing and the mail clerk zip code keyboard entries. The console card is responsible for loading the keystrokes from the mail clerk into the general interface card FIFO buffers and generating a timing signal called buffered lockout to initiate EZR processing of the mail piece. There have been 4 versions of the console card deployed by the Postal Service over the life of the EZR design. The problems of the initially deployed card, Type 1 and Type 2 post-deployment cards, were a verified variety of mix of mail clerk keying problems and signal noise problems. Even the Type 3 card, now in wide deployment, has many problems that were addressed by the EZR2 console card. A description of these problems will be made during the review of the EZR2 replacement card. The next card is the bin trip interface card. This card is simply a 16-bit input-output buffering, which controls the 15 bin trips of a module's level. There are 3 cards, one for each level of bin trips in the MPLSM. The bin trips open the cart doors to perform mail sorting in the EZR design. Additionally, the card interfaces to the bin full sensors of the MPLSM. These are read as a word representing the 15 bin full sensors. It should be noted that only the bottom 2 levels of the 3 levels in a module contain bin full sensors. This is due to the fact that the top level of bins uses a chute exiting system which prevents the requirement for a bin full system. The next card is the chain position sensor card. This card interfaces 4 rotary encoder and 0 position sensor arrays, 1 array per level of the MPLSM. The rotary encoders measure the chain link motion on each of the 4 levels of the MPLSM. The encoder data provides the information needed to determine alignments in the MPLSM. This alignment information is used to control the mail sorting operation of the MPLSM. The CPS card is replaced in the EZR2 design. The remaining 6 bay control racks are similar, except they do not have chain position sensor cards, and the end modules have only 1 console interface card to match the single console in these modules. Next, we'll look at the EZR2 kit upgrade area, block diagram. The EZR2 design was developed as an upgrade kit and as such was intended to be placed into the existing EZR machine. The Level 3 technical data package has been laid out to allow integration into the EZR TDP so that complete EZR2 and EZR components could be manufactured as a single kit. The EZR printer was replaced in the EZR2 upgrade for 2 reasons. First, the existing printer did not support IBM printer interface code standards. This would have made code interchangeability a problem, as it has done for the EZR display terminal. Second, the EZR printers are very old and needed to be replaced. The EZR2 deployed under the development contract used Okidata 293 wide carriage dot matrix printers. The wide carriage feature was provided to allow the wider, more complicated data collection reports and may only need a standard carriage with the production deployment. Next, the supervisor terminal, disk box, and alarm panel are replacing the EZR2 by a process control computer. Unfortunately, there has been an impression that this is a desktop personal computer, or PC. This is not a valid assumption. First, the workroom floor is a moderately hostile environment for a desktop PC. The Intel 301Z box used is designed for value-added process control applications and is designed for operation in this type of environment. The Postal Service and GPRD tested 7 different computers, 5 of which were desktop PCs provided by the Postal Service which did not function properly. The coprocessor card, which is located inside the process control computer, replaces 5 of the cards in the central control rack. The small size of the coprocessor card is due to advanced technology and considerable development work by GPRD. The card uses an embedded 8186 16-bit microprocessor operating at 12 megahertz. The processor can sustain 1.5 million and burst to 3 million instructions per second. The coprocessor is programmed in native assembly language and has no operating system overhead. The disk interface card of the central control rack was not replaced by the coprocessor, as the process control computer provides disk interface functions. All mail sorting, edit, and data collection operations are performed by the coprocessor. There was considerable thought early in the development to place the coprocessor into the central control rack. This would have eliminated the cabling changes and power supply revisions of the EZR2 upgrade installation procedure. The disadvantages were the harsh environment and slow communication speed to the user interface terminal. By placing the coprocessor card in the process control computer, we had a less harsh environment and high-speed operator display interface. During beta test, software crashes of the Xenix operating system and the process control computer did not affect the coprocessor, as it would continue to run. The site continued to sort mail to the end of tour or to a break, where we could reset the failed process control computer or software. The idea that the coprocessor, a simple I/O card of a PC, underestimates the complexity of the coprocessor card design and the software running in the coprocessor card. Next, the console cards of the EZR were replaced with the new EZR2 console interface cards. These are shown physically, as we're panning here, along the actual length of the MPLSM. The EZR2 console interface cards are microprocessor-based and use digital signal processing firmware to eliminate many noise and keyboard interface problems of the EZR2 console interface. The design of the console card also was influenced by the desire to use barcode readers, barcode printers, asynchronous console operation, and alphanumeric keyboards with the MPLSM consoles. The chain position sensor card is also replaced as part of the EZR2 kit. This was done to allow improved chain link resolution, noise suppression, and future advanced maintenance diagnostics and link correction algorithms. The CPS card is also microprocessor-based and uses digital signal processing firmware. The digital signal processing provides improved accuracy, noise immunity, and extended interface features. This EZR2 CPS card also interfaces to the local area network bus to allow full duplex communications to the coprocessor card. Note the local area network bus that connects the coprocessor card to the console and CPS interface cards. This network is a simple twisted pair shielded cable that loops from the coprocessor to the bay control racks in order to the last bay control rack. The last console card has a jumper-enabled resistor terminator to terminate this network cable. The network allows data transfer using packet protocol at 3,000 bytes per second rate. It should be noted that at this time, the network cable has been removed from the production deployment against the recommendations of GPRD. A spares kit of 1 coprocessor card, 1 chain position sensor, and 1 console card, 2 console cards was provided to the sites. This spares kit was based on the deployment of a single EZR2 kit to each of the beta test post offices with a 24-hour repair and support procedure provided by GPRD. A realistic spares deployment, even though the machines at the beta test sites work well, is the typical 20%. The reliability of the beta test site equipment was achieved by 48-hour burn-in and in-circuit testing of the EZR2 cards in a full-function simulator before shipment from GPRD. Additionally, the sites were each debugged of existing MPLSM EZR problems by GPRD to allow the MPLSMs and the existing EZR components to start from a very clean standpoint. The upgrade kit also contains the Xenix operating system software and the EZR2 application software. An installation manual and handbook were supplied to the beta sites under separate delivery. Next, we'll look at the coprocessor block diagram. The coprocessor block diagram shows the EZR2 coprocessor is designed to occupy a slot in an industry-standard architecture ISA 16-bit bus defined to the IEEE P996 standard. This is the bus standard used in the AT class computers and many of the industrial value-added process control computers like the Intel 301Z box used in the GPRD deployed beta EZR2 test sites. The coprocessor card bus interface logic allows access from the 8386 process control computer to the 8256 MUART. The MUART is a multifunction asynchronous receiver and transmitter and is a complex interface circuit. This interface circuit has 5 timer counters, a full duplex serial port, 2 parallel 8-bit ports, an 8-level interrupt controller, and finally a vector interrupt bus interface. The timers and interrupt controller of this part are used to provide the interrupt communications exchange between the coprocessor and the process control computer. This eliminates the processing overhead of simpler polled approaches. The timers are dual purpose, providing time task interrupts to the Xenix EZR driver code and to operate as a watchdog timer for the coprocessor. The serial port of the MUART is used at present to output raw data collection information in a format usable by external systems like the Real-Time Information Monitoring System, called RIMS, and the Distribution Information Services, called DIS. The parallel ports of the MUART are used to provide master control of the coprocessor reset and management signal lines. These are used during the initialization of the coprocessor and then left dormant until another power-up sequence or reset and reload of the coprocessor card. The I/O interface logic is used to arbitrate between the coprocessor access to shared resources using the ISA handshake procedures and the 8386 processor of the process control computer accessing the shared resources on the coprocessor card. The small block is actually about 1/3 of the coprocessor card components and contains 4 custom program logic array integrated circuits. The logic in this element was the most difficult to develop and most important, prevent lockups. This lockup occurs when both processors request a service at exactly the same time and was a major development problem in the EZR2 project. The heart of the coprocessor is the enhanced Intel 8186 embedded processor. This processor contains a 16-bit high-performance microprocessor core, 2 1 megabit per second transfer DMA access controllers, 3 16-bit timer counters set for timing events from 10 microseconds to 36 seconds, an 11-level interrupt controller operated in the real-time multitasking nested mode, and reset and clock support logic. To make this a simple discussion, the addition of the 1 megabyte of memory located in the adjacent block, and you have the master processor and sort processor of the central control rack EZR design. This block should not be underestimated. Intel supplies 3 books to document this one 84-pin multiplex part. One part of the manual's documentation is for hardware design, one part is for software, and one part is for how you try to use it. While we are discussing the 1 megabyte of memory, which is located just above and to the left, we will discuss the allocation of this memory under the EZR2 software. The first 64 kilobytes are used for stacks, edit, and the real-time data collection process. The EZR2 design collects every event that occurs in the EZR2 equipped MPLSM and stores this with timing to the nearest millisecond. At fixed intervals of 36 seconds, which is the Postal Service data and labor reporting base of 1/100th of an hour, the stored data is transferred from this temporary memory area in the hard disk to the hard disk of the process control computer every 36 seconds. The top 64 kilobytes is allocated to the control program and is used to process the mail of the MPLSM. There are some special memory allocations in this top memory for semaphores and data transfer between the process control computer and the coprocessor. Finally, the remaining 896 kilobytes of memory is allocated to sort scheme storage and use. This may at first seem to be a large amount of memory for sort schemes, but when divided by 12 to allow separate sort schemes for each console as needed under secondary operation, the memory allocated to a console equates to only 74.6 kilobytes. This is the reason for a crossover point which exists to place the alphanumeric extraction-based sort schemes into the 256 kilobytes of the console cards, which can be expanded by the addition of 2 memory chips to a capacity of 512 kilobytes for memory translation on a console-by-console basis. Next, the EZR bus interface logic contains the components used to interface the high-speed bus of the 8186 processor to the moderate-speed bus of the 13 twisted pair bay control rack interface cable. This logic was designed to allow direct access to the bay control racks of the EZR without software overhead. This is done by a custom program logic array integrated circuit that performs conversion between the 8186 bus timing and control signals and the EZR bus timing and control signals. The final block is the dual 82530 serial interface part. This part provides 2 full duplex async and synchronous serial channels which can operate from 50 baud to 1 megabaud. The part includes support for the Intel BitBus high-speed network using the RS-485 packet transfer protocol. One of these serial ports is dedicated to the local area network connecting the 12 console and chain position sensor cards together. The other serial is buffered to RS-232 signal levels and provided as a general-purpose expansion serial port. This has been tentatively reserved for communications with a central OCR address conversion database computer access port. Next, we'll pan to and look at the CPS card block diagram. The next card to be viewed is the chain position sensor card. The block diagram of this card includes the remote-mounted rotary encoders and zero position sensors for reference. The CPS card provides the alignment information of the MPLSM for calculating sort timing information. The MPLSM geometry is defined in terms of chain links and for accuracy in fractions of links. This card uses an embedded 64180 microprocessor based on the Hitachi high integration processor core. This processor core contains a ZD instruction set microprocessor with extended 16-bit instructions, 2 direct memory access controllers, 2 16-bit timer counters, 2 async serial ports, 1 synchronous serial port capable of 1 megabaud data transfer rate, and 512 kilobyte memory management extension to the Z80 processor core. This embedded processor is supported by 8 kilobytes of read-only memory that contains the firmware to simulate a standard EZRII CPS card and 8 kilobytes of random access memory to provide working memory storage. The firmware provided under this contract supports emulation of the original EZRII CPS card so that the card can be retrofitted to the old EZRII design. The reason was the ability of this card to solve many sort accuracy and noise problems caused by the static electricity problem of the MPLSM. The EZRII interface is simulated by a 4 by 16-bit dual-port register array. This is the same output-only interface method of the existing EZRII CPS card. Full duplex operation of the CPS card in the EZRII was not provided. This was due to the local area network interface, which can communicate in a bidirectional manner to the coprocessor card. One feature of the new card is the ability to synchronously update all of the alignment data register array without having partial update data read by the coprocessor, or for that matter, the old communication bus controller card of the EZRII design. This was a major problem with the old card, as you can read the upper byte during an update that crosses from the lower to upper byte and then read the lower byte and obtain a read error of over 16 links. This causes popcorn tripping of the MPLSM and can missort mail to the wrong bin, as well as cause mail to go to the zero bin. A display made of 4 hexadecimal digits is supported to simulate the diagnostic displays of the old EZRII card, along with a rotary thumb wheel switch. The EZR2 cards deployed have decimal binary coded switches, although for the production, GPRD has recommended that these switches be changed to hexadecimal coded switches. The firmware has been programmed to provide not only the original EZR hexadecimal display of link count, but also decimal decoded and scan direction diagnostic displays. These are accessed by various settings of the thumb wheel switch. It was found during our testing that the additional 6 conditions provided by the decimal switch do not provide enough readouts for all of the diagnostics we wish to provide. The parallel I/O block performs the interface between the processor signals and the digitally processed inputs. Note that there are no counters or other logic on the CPS card. All data is digitally signal processed. The counters of links and zero alignments are processed by firmware that enhances the signals to remove noise. Then the data is processed to use the full rotary encoder capability of the rotary optical encoders to obtain 1/32 of a link internal accuracy and report externally to 1/16 of a link on the parallel bus. Note that if the coprocessor to CPS connection via the local area network is available, the full 1/32 of a link accuracy is also available. Unfortunately, to be old EZR compatible, the EZR2 CPS card defaults to the 1/8 link reporting, and since the local area network is no longer available, the card cannot be switched to the high resolution mode. This is one of the many reasons that the local area network cable needs to be fielded in the production design. The CPS card serial ports are buffered to provide RS-485 network interface and 2 RS-422 buffered local serial ports for future expansion. These are initially committed to the barcode reader or printer and to control for the asynchronous console. An asynchronous console with barcode printer, which has been developed and tested on the MPLSM by GPRD as a subcontractor, GPRD was a subcontractor and developed the control electronics for this asynchronous console test. The advantage is the ability to convert the MPLSM and console into a rather low-cost code desk with a single level of sort. Next, we'll pan to a block diagram of the console interface card. The block diagram of the console card is more sophisticated than the CPS or coprocessor, but in fact is the simplest of the cards in actual design. The console card uses the same embedded processor as the chain position sensor card. This allowed common parts and software development. The major difference is the support of random access memory. A standard 256 kilobytes of memory is provided on the console card and is expandable to 512 kilobytes by the addition of 2 memory integrated circuits. The large amount of memory allows the console card to perform complicated alphanumeric extraction keying algorithms and direct barcode extraction operations. Additionally, the processor can spend more time to perform the lookup, as the process can be overlapped with that of the operator key entries rather than having to wait to the narrow timing window presented by the coprocessor lockout sequence. The coprocessor can dedicate no more than 500 microseconds in a conversion cycle, while the console card can use over 200 milliseconds of processing. The coprocessor card can in fact spend enough time that accuracy of the mail sorting is degraded. Our tests in Oklahoma City indicate that 5-key extraction point is right on the edge of placing the coprocessor card over this timing edge. The method of input buffering in the console card is very significant. The existing EZR console cards and other pre-ZMT attempts to access data from the piano parallel keyboards have been scanned approaches. The problem with scanned approaches to the keyboard is the speed and manner of mail clerk keying entry. Mail clerks key very fast. In fact, tests done in 1979 show that operators hit adjacent keys as close as 5 milliseconds apart. This is predominantly due to the parallel nature of the keyboard. This causes transposed keying and keying errors on the MPLSM when scanned keyboard systems are used. These types of transposed keys errors are very hard to test for, as they almost always result in a missent piece of mail and not a keying error. Additionally, the scanned nature did not provide the keyboard with sufficient contact cleaning current. This current flows to keep oxides from causing intermittent switch failures. Most important, the scan interface only uses half of the output from the signal switch. As a result, the differential output of the switches, which provides noise immunity in the EZR2 card, is not used in the present EZR console interface card. This is significant since the cable from the keyboard must parallel with 3 feet of 120-volt controlled solenoid signal cables and is not shielded. The EZR2 console card solves these problems by using the ZMT method of parallel key entry. Each key switch has a separate interface support circuit and pull-up resistors. Second, the output of the input demount circuits is interrupt serviced so that key entries can be as close as 100 microseconds apart and not transpose. Additionally, the card can accept any number and order of keying, i.e. infinite key rollover and key depression. The decimal LED displays of the EZR console card have been duplicated and additional diagnostics have been added. Particular attention was paid to lockout. The lockout status is now displayed by an LED so that verification of this signal can be made without test equipment. The lockout signal has had a noise problem even from the introduction of the optical disc-based encoder of the ESP design. To solve these problems, EZR2 console card incorporated both analog and digital signal processing to filter the lockout signal. Now that the basics of the EZR design are understood, let's talk about some of the trade-offs associated with modular selection. First, the process control computer is not an option. It must be present, and filling a desktop PC would be a significant problem. The Postal Service, in search of a low-cost computer for the EZR2, tried 5 different desktop PCs. These computers were tried in the various test sites, including Oklahoma City. All 5 of these desktop PC machines failed in one way or another. Electrostatic problems killed 2 of the machines. Even low static gun tests of 15 kilovolts would crash the machines in the workroom floor environment. The workroom floor is a very harsh electrostatic area. The present EZR process control electronics have significant problems with electrostatic discharge. Remember that the MPLSM is moving paper in plastic carts and builds up large static potentials. To give a reference of how bad the problem is with the EZR and static, be advised that almost every office that we have installed and tested EZR2 upgrade kits had a different static solution. Some were as bizarre as loading a daily supply of cling-free dryer cloths on the end section sprocket shafts to reduce the static discharge of the carts, and others had ion gun dissipators. In fact, until the use of the EZR2 CPS card and console cards, most of the offices could not install a complete set of 161 plastic carts in the MPLSM. The offices were mixing metal carts with plastic carts on a 1:5 ratio to dissipate the static discharge built up along the conveyor assembly. Finally, an ALR 8386 machine of the Process Control Workstation machine class was provided. While the desktop version of the ALR computer worked, the cabinet would not accommodate the full-size AT format coprocessor card. A freestanding tower version was tried and worked. Even though this machine worked, it had only a very short field test, and how the design will stand up over time needs to be evaluated, and in particular tested to the acceptance test criteria. The coprocessor card must be supplied as the EZR software, and for that matter, almost all extended features of the EZR2 are channeled through the processing of this card. In fact, it is impossible for this EZR2 system to work with just a PC. A Hayes-compatible 2400 baud modem is provided in the design and supported by the EZR2 software. The modem is optional and can be removed from the deployment. The modem was intended to allow remote access to the data collection information and remote diagnostics. The present feeling is to not deploy this modem, although GPRD feels that even if you do not use it at present, it would cost more to deploy it at a later time than to install it as part of the present deployment. The local area network cable from the coprocessor to the EZR2 console and CPS cards is an optional feature. The cable in GPRD's feeling should be deployed, as many features of the EZR2 design are not possible without this cable. For example, the higher resolution of the EZR2 CPS card is not available unless firmware changes are made to the CPS card. Most important, the ability to use the console cards as originally planned for alphanumeric extraction keying is not possible. The chain position sensor card can be optionally deployed. The new CPS card speaks for itself, as GPRD has been requested to supply the EZR2 CPS card for the older EZR MPLSMs to solve the static problems. The reason for this exchange of the CPS cards is simple. During the test at the 12 test sites, it became apparent that the EZR CPS card does not accurately align the zero position to achieve the 40 pieces out of 3,000 sort error rate required by the acceptance test. This is using the maintenance edit automatic keying so that no console or mail clerk error is included. When the console card is also accounted for with the lockout and key transposition problems, it is very difficult to achieve the acceptance rate. Also understand that the EZR2 as tested, except Northern Virginia, which had special problems, were able to exceed the test levels of the acceptance test by significant margins when the EZR2 cards were used. The console card is also optional, but there are many features and reasons that such as the extraction keying for the deployment of the new console card. The lockout signal problem and the keying problems of the existing console cards are significant. In particular, Double lockout problem can be attributed with 1 to 3 errors per 1,000 pieces of mail sorted. This is based on data collected by the new EZRII data collection. The console card implemented digital signal filtering on the lockout signal itself, and also a setting up of a flywheel timer of 3/4 of a second has prevented double lockout. Double lockout appears as mail that has not been keyed and is very hard to test for with the EZR design. Another feature of the console card is the ability to adapt to new keyboards. The presently fielded Hall Effect keyboard is an example. When the Hall Effect keyboard is first installed in an MPLSM, the key error rate increases. When this occurred on an EZR2-based MPLSM, the error rate of mail clerk keying went up to over 10%. A quick check revealed that the new keyboard has almost no hysteresis. The small movement between key to press and not to press allows the mail clerk to accidentally double key keystrokes. This missends mail and reduces productivity. Mail clerks have been able to circumvent some of the keying error by special keying habits, but even then the error rate does not return to the pre-Hall Effect keyboard level. The EZR2 console card has a simple solution. By changing the firmware, we can filter the key acceptance routine. This routine would allow only different keys to be keyed closer than 50 milliseconds and require a 50 millisecond guard timing window for the same key. The console card is also the basis for console-mounted barcode reader, barcode printer, and asynchronous console capabilities of the EZR2 design. The design and modification plans for the asynchronous console belong to the Postal Service and were done in late 1986. Another reason to keep the console card is a more flexible method of using barcode readers with the EZR2 design. The presently deployed MPLSM barcode reader design allows only one console in a module to be modified. This means that only 6 consoles can have a barcode reader, and they must be spread to every other console. By spreading the consoles in this manner, it makes ledge loading of the machine difficult and inefficient. The present design also requires separate control and sort scheme loading at each console rather than from the central control of the EZR2, further reducing productivity. The EZR2 console card allows either 6 barcode readers on adjacent consoles or a complete 12 consoles to have barcode readers. Control and loading of the sort schemes can be made from the supervisor central control display. Additionally, the data collection of the barcode distribution can be made through the data collection system of the EZR2. As of now, the present barcode reader design prevents such data collection. In general, the deployment of the barcode readers or extraction keying would, in our recommendation, require the use of the EZR2 console card. It is possible to implement the alphanumeric extraction keying without the EZR2 console card. GPRD has test software package in Oklahoma City Post Office that will accept 4 and 5-digit alphanumeric keying from the standard 20-key piano keyboard. This is done by overlapping 6 letters to share the same key. Our experience with Oklahoma City sort schemes and the test development of sort schemes for San Diego, Louisville, and Boston indicates that each site needs to assign the 26 letters to 20 keys differently to achieve a reasonable number of memory items. This is a result of ethnic and area street naming by region of the country. The memory items are a result of conflicts that cannot be resolved by only 2 or 3 letters of the street and the 2 numbers of the street number. Mail clerks must recognize these conditions and key a special sequence for the exception. We also found that the first and last character of the name is the best approach, as the second letter is almost always a vowel. This meant that the second letter was almost always from a set of 6 rather than 26 possibilities, and this significantly affected the conflict resolution. Another item to be decided is whether the keying will be citywide or zone-based. Citywide decoding is the typical OCR approach and works well as the whole street name and number is available. The mail clerk will only be keying 2 or 3 letters of the street name and 2 digits of the street number. Our experience indicates that 2, even 3 letters, is not enough in citywide extraction keying. In fact, the test of program scanning indicates that 6 or 7 letter keys would be required to achieve full citywide zone decoding. Zone sorting reduces the conflicts by the street, block number, range, direction, and in large cities, by overlap of 10,000 street numbers. The zone isolation features is what makes the 2-letter and 2-digit alphanumeric extraction key work with less than 100 memory items. This is the maximum number of labor union agreed memory items per sort scheme. The fact is that the same street letters with the same block number range is rare in a zone, but not in a city, results in the primary reason for zone sorts working and citywide not working at low keystroke values. More important is the resolution of north, south, east, west, and other general decoding by the zones, which took this into account during the development of zip codes. GPRD developed some internal software to take the carrier route information system, or CRIS files, and to generate analysis for the alphanumeric extraction key. In fact, we developed software which allows us to generate complete sort schemes without operator or site intervention. Additionally, the software was added to allow editing of the database so that special conditions could be taken care of by the sites. Much of our reasoning is based on actual data reduction and site usage and should be considered as significant. A second approach was looked at in Oklahoma City, and this consisted of no memory items for the untrained alphanumeric mail clerk. The clerk would key out memory items without memory items, and any conflicts are separated to a conflict bin. The mail collected in this conflict bin is then sorted by a trained mail clerk using memory items. Our experience was a typical memory item count of 5 to 25 for Oklahoma City's zone sort scheme operation. This allowed a memory item trained mail clerk to support about 5 untrained mail clerks. The citywide sort can be achieved by using the console interface card in an interactive translation mode. By having the card perform lookup as the keying is taking place, the card can allow the varying length extraction keying process. The first keys would be the street number, and the remaining would be the street name and direction information until a conflict resolution was achieved. This means a variable number of keys would be entered, allowing some decodes at short lengths and some at long. The keyboard would have an indicator to indicate when the keying was sufficient or the key entry time ran out. The use of the asynchronous console would be the best approach, as the mail piece would remain until it was decoded, and when decoded, the advance of the mail piece would indicate sufficient keying. The EZRII is modular and uses distributed processing to provide many advanced features. While many of the distributed process modules can be removed, the load and limitations on other elements of the design cannot continue to provide the performance that the 12 fielded beta test sites have shown. I hope this general discussion of the ad hoc developments made during the EZRII project will provide you with an understanding that the EZRII is a very capable upgrade if deployed properly. The installation, training, and overall operation of the 12 fielded beta test sites indicates that the EZRII can be a very effective upgrade.
The first step to install the EZRII is to remove the components of the EZR that will no longer be used. The first components are the supervisor's panel-mounted disk box and alarm panel, which require 2 personnel to remove. This consists of removing the cables from the components and then unbolting the cabinets from the supervisor's panel. Next, the supervisor's terminal must be disconnected and removed. The cable from this terminal and the printer are common. The printer is disconnected and removed next. The cable is then fed back to the central control rack for future removal. Next, the central control rack and associated cables are removed from the MPLSM. This process takes approximately 2 hours and consists of unwiring the power, signals, and backup support cables from the rack, and finally the removal of the racks themselves. The central control rack is also powered by separate power supplies, which are removed and set aside. Removal of the console and change position sensor cards is done next. This completes the removal of the existing EZR components not used with the EZR2 upgrade kit. The new EZR2 chain position sensor interface card is installed in place of the removed EZR interface card. This new card will require the checkout and adjustment of the CPS encoder and zero detection components to obtain best accuracy. The 12 EZR2 console interface cards are next installed to replace the removed EZR console interface cards. The console card requires adjustment of the lockout disk and verification of the proper keyboard cables to operate properly. There are versions of the keyboard cable that are not compatible with the EZR2 console interface card. Additionally, there are various versions of the general interface card of the EZR that are not compatible with the EZR2 console card. These general interface cards need to be replaced. The coprocessor card is installed into the process control computer's protective housing. This gives power to the coprocessor and protects it from the moderately harsh environment of the workroom floor. The coprocessor is where the 13 microprocessor-based console and chain position sensor cards throughout the MPLSM communicate to. The coprocessor is the most important part of the EZR2 system. If this is not set up properly and supported properly by the process control computer, the EZR2 will not function reliably. The process control computer is next installed on the supervisor's table in place of the EZR supervisor terminal whose function it replaces. The cable from the bay control units is then connected to the coprocessor card inside the process control computer. The new EZR2 dot matrix printer is then installed next to the process control computer. The interface cable from the process control computer to the printer is then installed. The new power backup unit is installed and connected to the process control computer also. The power cable from the backup power supply is run to the center module of the MPLSM and terminated with connectors. The postal supplied 12-volt power supply is used to power the chain position sensor subsystem. This power supply is now installed at the C3 module. The power backup supply cable is then connected to this 12-volt power supply. Wiring for the 12 volts of the bay control unit are disconnected and removed. The new power supply is then wired in place of the removed 12-volt wires. This installation is now tested and debugged using a procedure developed by Great Plains Research and Development in concert with the Postal Quality Assurance personnel. This procedure provides a complete test of the MPLSM and EZR2 upgrade operating in unison. The test requires the ledge loading, sorting, and sweeping of over 3,000 pieces of mail with a complete audit of all sorting operations. A maximum of 48 pieces of missorted mail is allowed for the test to be successful. On average, GPRD installed machines had less than 3 pieces of unaccounted for mail sorting errors. Any problems found during this test will require debugging and correction of the problem or problems before the MPLSM can be turned over to operations for live mail sorting.
Training of the EZR2 upgrade kit system at each of the test sites was part of the development contract requirements. GPRD was responsible for the development of training of the EZR2 project. Training of the personnel at each test site was conducted to determine what level of training was needed to provide the offices with uninterrupted mail sorting operation and maintenance support. This training was developed along with training materials by Great Plains under initial requirements of the development contract. The contract specified a 2-day training class with separate coverage for operations and maintenance personnel. Written tests were conducted at the end of the training classes along with surveys regarding the training procedures and material covered. These classes were arranged to have a combination of operations and maintenance class the first day. This class covered EZR2 elements common to both operations and maintenance personnel. The second day class was split with operations personnel given instruction in the day-to-day operation of the EZR. The maintenance personnel were given training on revised diagnostics, troubleshooting, repair, and alignment procedures of the EZR2 upgrade kit. Our experience with the training revealed many successful aspects of this method of training, as well as some problems. The most significant feature was the ad hoc interaction with the students and their interest in the advanced features of the EZR2. This was followed by the low downtime of personnel by having the classes at the post offices. The most asked question was, what does the EZR2 provide operations and maintenance that the EZR did not provide? This question varied from site to site, as the EZR2 does many functions of which only some are of interest to a particular post office. The ad hoc nature of the training allows tailoring of the syllabus to meet the particular post office interest. This question is important because the EZR2, while being very easy to operate with its point-and-pick menus, has many new features. Those features needed to operate the EZR2 in place of the EZR were covered first, and then, as time permitted, the extended features of the EZR2 were covered. The 2-day class presented a problem as the classes covered only the basics of how to operate the EZR2 in place of the EZR. The training classes are about 1 to 2 days short of the effective time required to train the postal personnel. The most significant problem discovered in the training aids was a lack of real-time display of the EZR2 screens. This can be solved by using a projected display of the EZR2 main console screen, and this can be achieved in future training with an LCD overhead display module or video projector that allows the display of CRT graphics on a projector screen. With this connected to a simulator-operated EZR2 process control computer, the many interactive graphics and display features of the EZR2 can be explained. More hands-on time of the actual MPLSM is needed for both supervisors and maintenance personnel. This training was conducted at most of the post offices. The limited time allowed only very crowded and chaotic access to this training. Extra time with smaller groups are needed to be effective. A spreading of the number of personnel and more time would solve this problem. The most significant problem was the scheduling of the training classes. All sites were sent instructions about the classes at least 2 weeks in advance. This still did not solve many schedule conflicts between the supervisors, maintenance, and operations personnel with attendance of the class. Great Plains, as a result, held as many as 3 classes at one site and usually 2 classes at the remainder of the postal test sites.
I'm Kevin Johnson, one of the programmers of the EZR2 software. We're going to take a look together at the EZR2 and how we've simplified the operation of the LSM equipped with the EZR2 upgrade kit. All interaction with the EZR2 can be achieved through the main console display and the keyboard. Due to the multi-user nature of the EZR2, it is also possible to use the EZR2 from the remote modem or the RAT terminal, which is the roll-around terminal. The EZR2 software provides a multiple-function window-based display interface. The display is divided into 4 windows, with the upper left window used for all user interaction. This window contains the EZR2 login screen display that is normally seen when the supervisor approaches the EZR2 console. The user interacts with the EZR2 through the keyboard via pick-and-point operations. This interaction window is also available to all remote access displays. Being logged into the EZR2 design is not required for the EZR2 to sort mail. Mail sorting is a separate process performed by the coprocessor card. The coprocessor card performs all EZR2 sorting and machine control and is supported by 13 microprocessor-based console and chain position sensor cards. While the coprocessor is located inside the process control computer, it functions separately from the process control computer. The display and keyboard of the process control computer are used as a terminal of the process control computer-based user interface software. Because of this configuration, the EZR2 has no separate maintenance and sorting modes as in the EZR design. To log in, the supervisor enters his or her name and password. The supervisor then has access to control the EZR2 at the level specified by his or her login authority. This authority is specified by the Post Office's local process control computer security officer, who performs all system administrator functions. The system administrator of the EZR2 creates a unique login name and password for each supervisor. This name and password creation with authority is also done for maintenance personnel and sort scheme management personnel, providing access to those elements of the EZR2. After the supervisor is logged in, the user interaction window displays the main menu screen. The user is only presented with those options that he or she is authorized to use. There are 3 main access levels usually authorized for the supervisor access. These provide all functions needed for sorting mail, performing edits, and developing reports of the LSM software. To select the function or submenu, the user presses the up and down arrow keys to highlight the desired option. As each option is selected, a short help description of that option is displayed at the bottom of the interaction window. Let's prepare the EZR2 equipped MPLSM for mail sorting as a demonstration to the user the interaction of the EZR2 software. First, we will highlight the Sort Scheme Control submenu option and then depress the Enter key to make this selection. This results in a new menu display with the first option line highlighted. The present EZRII software is written to allow a depth of 32 such menus. Each of these menus can have 7 functions or further submenu selection options. The sorting of mail on the MPLSM requires that a sort scheme to translate the key entries by console operators to bin destinations. These must be loaded into the coprocessor and assigned so that the coprocessor can perform its sort function. This is done using the sort scheme control menu, which is highlighted and will now be entered by depressing the enter key. The EZRII software allows a variety of sort schemes to be used, and these must be loaded into the coprocessor for actual console sorting. Remember, the process control computer is used as a terminal in a disk storage unit. The actual sorting is done by the coprocessor and its support cards in the MPLSM. To accomplish loading of schemes, the coprocessor, a menu function has been created to load the sort schemes in the coprocessor. Upon highlighting and selecting this function, the software scans the sort scheme hard disk directory. The schemes are sorted in alphabetical order. Then all schemes already loaded into the coprocessor are removed from the list. The supervisor is then presented with an alphabetically sorted list of sort schemes. To simplify operations, only the sort schemes not loaded into the coprocessor are displayed. The user next highlights each sort scheme to be loaded and tags the sort scheme by depressing the T key. As each scheme is tagged, it displays a T next to it to indicate it will be loaded. As there are more than 6 schemes displayed, the user is given the option to scroll through more by using the page up and page down keys. After all sort schemes to be loaded are tagged, the user depresses the escape key twice. This brings up the option of using the tagged files for loading or to exit without using the tagged files. We will load the files, so we depress the U to use the files. Note that as the files are loaded to the coprocessor, a display shows the actual loading status. The coprocessor can hold a total of 32 sort schemes at a time, and if the attempt to load more is made, the status error message of the unable to load will be presented. Next, to sort mail, the sort schemes need to be assigned to the consoles of the MPLSM. This is accomplished by the assign sort scheme to console function. The console to be set is highlighted and the available sort schemes scrolled by using the page up and page down keys. Note that at no time does an operator have to know the names or spelling of the sort schemes. To select all console to a single scheme, the insert key can be depressed. This key assigns the present scheme to all the consoles. The escape key is depressed twice, and then the activate key is pressed to accept the new assignments. Now that the schemes are assigned, the supervisor needs to set up tour information and start data collection. Tour information is set to allow the report generated by the EZRII to contain actual productivity information, as actual personnel and times are available. Data collection takes place at all times because the coprocessor is always collecting data. The act of setting the data collection status is used to make the generation of reports at the end of the tour simple. By turning off data collection, a report of the tour from start to end times will be generated without the supervisor having to enter the times. Additionally, a report for any period of time can be made after the fact by entering the start and end times. The MPLSM is now ready to sort mail and data collection for the tour. The supervisor is responsible for maintaining the personnel numbers for the complete tour. This allows reports to be accurate to 1/100th of an hour. This startup procedure takes only 30 seconds. The remaining 3 windows of the EZRII display are used for the real-time status display of the EZRII. There is no equivalent to these in the EZR design. The coprocessor performs all real-time processing for mail sorting. This leaves some spare processing time for the display terminal. The processing is used to display status generated by the coprocessor. By interpreting this status, it is possible for a correctly trained supervisor to manage an MPLSM better than with the EZR. Significant productivity improvement can be achieved by proper interpretation and management using the EZRII. This is a side benefit of the advanced data collection and analysis features in the real-time display. The first window located below the user interaction display is called the MPLSM status window. This window contains information relating to the overall MPLSM operation. This includes transport alarms such as letter on chain, letter on cart, and stop line activation as caused by the emergency stop cord. Additionally, the alignment information provided by the chain position sensor card and rotary encoder subsystem is displayed. The chain position subsystem values are not only displayed, but real-time diagnostics are available. These diagnostics can detect alignment problems and missort conditions. These include conditions that would be difficult to detect except with the continuing sample of the mail from the back of the MPLSM. These error conditions are displayed as needed in this window. Note that as long as there are no error conditions, the display area is blank. This approach is used through the EZRII display design so that the error condition stands out. The next window is the console status window. This window monitors the mail insertion function of the MPLSM. All 12 consoles are monitored, including all key entries, bin destination, and sort scheme status. When an operator is keying correctly, the right area is clear. When errors are decoded, an abbreviation of the error is displayed. This allows a trained supervisor to detect problems early before large amounts of mail are missorted. The supervisor can then use the status window along with the other EZRII features to determine if the problem is related to an operator or should be checked by maintenance. The lower portion of this window contains quick reference numeric statistics for use by the supervisor. These values can be used to determine if the correction taken has been successful. There are many modes in which some of the status displays can be operated as displayed here. The next window is the sweep side status display window. This window monitors the output side of the MPLSM. The status of console jams and their clear procedures are monitored. Console jams are cleared from the sweep side by sweepers. Additionally, the bin sweeping operation is monitored by watching for excess time to clear bins. The EZRII real-time status display is featured like alarm condition timing. When an alarm activates like a bin full, it is initially low-intensity fixed text. 30 seconds later, the alarm goes to high intensity, and after a minute, it blinks. This allows the supervisor to look at the display and tell if not only that the bin is not swept, but how long it has been full. I hope this quick tour of the basic EZRII software and real-time status display have been informative. While the EZRII software is easy to use for basic sort operations, many of the advanced features require considerable training and hands-on experience.
This end of contract review has provided as much detail as possible in a 1-hour video. This video does not attempt to discuss all of the problems, developments, and recommendations for the future of the EZRII design. We hope that this video and the information provided will assist in the productive and reliable deployment of the EZRII upgrade. Further information on items discussed in this video can be obtained from Great Plains Research and Development. The address and fax information will be provided at the close of this tape. Thank you for your attention and interest in the GPRD development of the EZRII upgrade kit.